Okay, let's start. So I'm going now to complete the derivation of a theory for path integral formulation in terms of coherent states. And I remind you that the problem we have in mind is that we have a set of particles, and the particles are bosons. So everything I'm doing until further notice is for bosons. We have some annihilation and creation operators. Sorry, this is not a good multiplication. So we have a set of A alpha and A alpha dagger creation and annihilation operators, and they satisfy the bosonic commutators. This is delta alpha prime, and we have some Hamiltonian that for the purpose of this class, the quantity that we want to calculate is a partition function describing the statistical mechanics of this many-body problem, where we are assuming that we are in the grand canonical ensemble. So there is a fixed temperature and a fixed chemical potential. And we define the grand canonical Hamiltonian to be a Hamiltonian minus mu times n, where n is the total number operator and h is the Hamiltonian that is written in terms of the A's and A daggers, and it is written in a normal ordered form. So if we write the most general form we have in mind, there is a single body part that we can write as something like that. Okay. This is a single body, and then there is an interaction part that sums over 4 indices: B, alpha, beta, gamma, delta. Okay, and in principle we can also have the 3-body and higher order terms, doesn't matter. And the number operator is of course just the sum over alpha, A alpha dagger, A alpha. Okay, so everything here is an operator expressed in terms of this, and we want to convert it into a path integral formulation of the partition function. And we saw that we can do it if we are using coherent states which satisfy the following definitions. So these are eigenstates of the annihilation operator with eigenvalues phi alpha. And the phi here, phi is a vector which contains phi alpha, some complex number for each quantum number. And the conjugate of this equation is that A alpha dagger acting on the left on phi gives you phi alpha bar. Okay, and phi bar is going to be the row vector of this. Okay, and last time we saw that we write. So this is all just a summary of of things that we already seen in the last week. And the point we got to is that the partition function, which is the trace of e to the minus beta h grand canonical, can be expressed as an integral over some coherent state eigenvalues of e to the this e to the minus beta h grand canonical, the diagonal matrix element in some state psi. And what we want to do now is to turn this integral into a path integral, just following the same idea that we used for the single particle problem before. Namely, what we do is we view the parameter beta, which is the inverse of temperature, as an imaginary time axis, and we divide it. We define here an imaginary time axis, which changes between 0 and beta, and actually, because during this imaginary time evolution, we go from one state to the same state. Actually, this coordinate, this imaginary time axis, folds on itself, and it's actually a circle. Okay, it's a circle that goes from 0 to beta, but the psi has to satisfy this. Okay, the psi initial and psi final are one and the same. Okay, so we want to think of the operator e to the minus beta h as evolution in imaginary time from an initial state coming back to the same initial state. Okay? So the idea is that we divide the imaginary time axis to small slots of size d tau, that eventually we're going to take the limit that d tau goes to 0, and we have, and then what we're doing is we already saw that because d tau is small, we can express the operator e to the minus beta h grand canonical as a product of many such exponentials, each of them acting on an infinitesimal time interval, and it's a product of total of n terms, where n here is beta divided by d tau. Okay, it's the number of time steps. Okay. Okay, so just writing it like this is you still have an operator, but now the idea is that in between each such exponential, we're going to stick the resolution of identity with some coherent state that we are going to label as psi j. So we define here an index j that changes between 1 to n minus 1, essentially. And it's going to be, and for each j, we're going to put a resolution of identity in between two such exponentials. Okay? So let me remind you how the resolution of identity looks like for coherent states. So let's just this is the total expression. Okay, let's assume that here somewhere this exponential is some j in between 1 and n. Okay, it's somewhere in the middle. So I'm putting resolution of identity psi j plus 1, psi j plus 1, e to the minus psi j plus 1, psi j plus 1, times psi j plus 1, psi j plus 1. Okay? And similarly, on the other side, let me draw it with a different color, perhaps. I'm going to put the same resolution of identity, but with psi j. Okay? Okay, so let me just write it quickly. So it's psi j. Okay. Change the e to the minus psi j, psi j. Okay. And I have here a big string of such products, and now I want to. So you see, as a result of this operation, what I get is that the operator e to the minus h d tau will be sandwiched between psi j plus 1 and psi j. Okay? And then the next one between psi j and psi j minus 1, and so on and so forth. So altogether, at each time step, what I'm getting is a product of two numbers or two expressions, which are the following. The jth step we end up having this exponential multiplied by the matrix element of e to the minus h d tau between psi j, j plus 1, and psi j. Okay? And of course, in the end, we are going to integrate over all these variables, all the psi j's. We are going to integrate over them. But inside the integral, what we have is a product over j of such things. Okay? You see, this is because this psi j plus 1 will already be acting on the, will be coupled to the next exponential, and this one on the next exponential. And I'm just left with this matrix element times the normalization factor. Okay? And that comes from, I remind you where that comes from. It comes from the overlap of psi j plus 1 with itself. So this is the basis of coherent states are is an over-complete basis where the norm is bigger than 1. It's an exponential of this thing, and therefore if we want a resolution of identity, we have to divide by it, and that's why we have this factor. Okay? So this is what we get in the end after we finish putting all these resolution of identities. What we get is the following thing. We get a product over J, okay, of such things, and I'm integrating over all these differentials. Okay? That's what we're going to get in the end. And let me write it more nicely. Hope it's okay to erase now, right? Yeah, I'll just erase this part. So what I'm getting is that this partition function can be expressed as an integral with a capital D. I will define it soon. Okay, I will define it soon. And then there is an exponential, sorry, no, not yet. Let me just write it first as a product. It's a product of J going from 1 to N, actually from, from 1 to N of e to the minus psi, actually, sorry, let me write it like this, so it will look more nicely, okay, psi j plus 1, psi j plus 1, and then this matrix element. Okay, that's the expression I get in the end. And everything here are numbers. Okay, but we have to explicitly find what is this matrix element. And we want it to be just a functional of the psi's. That's the idea, right? And then we just get something that in the end we'll be able to interpret as an exponential of some function of complex numbers. Okay? So that's the idea. And now we have to find what is this. And here you see why we chose the coherent states. Because what is the idea? Why did we choose the coherent states? Because coherent states are eigenstates of the annihilation operator. And similarly, these coherent states, which are eigenstates of the creation operator. And now here is the crucial thing, because we wrote the Hamiltonian and everything in the exponent in normal order, all the annihilations are on the right and the creations are on the left, right? And therefore, when we act with this when we take the matrix element, we get something where we can simply replace all we get an expression which is like the Hamiltonian, but everywhere, every A is now replaced by psi, and every A dagger by psi bar. Okay? So let me write something general to get you the idea. This we no longer need. You take any operator that is a functional of A alphas, So we write it like this, the functional of some A alpha dagger and A alpha. And it's normal ordered. So if you take its matrix element between some psi prime to some psi, okay, any arbitrary covariant state, because it's normal ordered, all the A's acting on psi prime will just give you a psi prime, and all the A daggers acting on the left will give you a psi bar. And what you're going to get is the eigenvalue, which is O psi bar alpha, psi prime alpha, times the overlap of psi and psi prime. Okay? So this operator is replaced by its eigenvalue, and you're still left with an overlap with the inner product of the psi prime and psi. Okay? And this is not a delta, because it's not an orthonormal basis, but what is it? It's e to the psi bar, psi bar. Okay? Is that clear? So again, here I have to calculate a matrix element of some operator, but this operator is normal ordered, and I can expand it as something that has A's on the right, A daggers on the left. All the A's acting on psi prime will just give you psi prime. All the A daggers acting on psi will give you psi bar. Okay? And so this will give you some number which has the same form of whatever you had in the expression O. And this number you can take out of the sandwich, and you're still left with the overlap. Okay? And this overlap is an exponential. Okay? And by the way, I'm just reminding that when I'm writing, this is a short notation for a scalar product of the vectors, because psi and psi prime are vectors of components psi alpha. So this is just sum over alpha. Sorry, must be sum over alpha of psi bar alpha psi prime. Okay, this is just a reminder of what I mean by this. Okay, so let's apply it here. So what is H grand canonical? H grand canonical is nothing but such an operator, right? And therefore the exponential of H is also like that, because what is an exponential of an, yes?
Is mu also a matrix?
Sorry, what?
So if
mu?
You are summing over alpha, mu, do you say that mu is the same for all alphas, or do you have also like a diagonal matrix?
What you mean,
yes.
This? No, mu is one parameter. Mu is just a chemical potential.
Yes, but
it's a single parameter.
Alpha kinds of particles.
No, they're not kinds of particles. Sorry, let me make it clear. Alpha is a quantum number of the particle. For example, it's the k vector. Okay, if you have
so far we
or coordinate, or I don't know, you have some basis of single particle state, but you have identical bosons. Okay, you have identical bosons, and they have some quantum numbers. Okay, like for example, for photons or photons, you have k. The vector potential so the vector. Not the vector potential. k vector is a quantum number if you have three particles, which is related to the momentum. So this is the alpha, but these are identical bosons, okay? And they have, and this is an expression for the number operator.
So all of this was for a single field.
And yeah, and the chemical potential is a thermodynamic parameter for one set of particles. Okay? It's like the temperature. There are two parameters here that are thermodynamic, mu and beta. Okay? Yes, so basically what I'm saying is that this matrix element, I know exactly how it looks. It's given by the exponential of, let me write it directly. So I'm just using this general definition and applying it. It's e to the minus h grand canonical of psi j plus 1 bar and psi j. Okay? And so it's whatever you get when you take, for example, I take this Hamiltonian and I write an expression where every A is replaced by psi j and every A dagger by psi j plus 1. Okay? And similarly here. Okay? So this is what this is. And now it's a number. Okay? It's an exponential of some functional of this field, but it is now multiplied by the overlap of psi j plus 1 and psi j. And this is e to the psi j plus 1 bar psi j. So altogether, what I'm getting, if I'm collecting everything, I get that z is going to be an integral which I will define. I still owe you a definition of this, okay? And here I have a product over J of, now it's going to be a set of numbers that all of them depend on J, okay? Now, and these are just exponentials. Everything here is an exponential. Okay, so I have a product of exponentials that depend on an index j, and I take the product over all j. So therefore, what I have is I can write it as an exponential of a sum over j of all these contributions, right? And now I'm allowed to do it because they are no longer operators, they are numbers. So e to the a times e to the b is e to the a plus b. Okay? Okay, so let's just write down what is the final expression that I get here. And it's going to be e to the minus, and now let me write it like this. So first of all, I have I have e to the minus sum over j, and then here I have, I'm collecting all the exponentials, okay? And I have psi j bar plus 1 times psi j plus 1 minus psi j, which is coming, the second term comes from this overlap, which is given by e to the psi j plus 1 bar psi j. Okay? So I have this exponential times this exponential. I can write it like this, collecting them together, with an overall minus sign. And to this I have to add the grand canonical, okay? Write the brackets as curly brackets. Okay? This is what I mean. Yes?
It's not the integral, not sigma.
So at the moment it's because J is a discrete index, it's a discrete index, therefore it's a sum. But because we are taking, and here I forgot the d tau. Here there is d tau. Okay. Because it's h times d tau. Okay, so it's a sum, but because we are going to take the limit that d tau goes to 0, it will turn into an integral. Okay, and the integral will be an integral over tau. Yeah?
פה יש לנו 4 אינדקסים של, כאילו, גם של יצירה וגם של השמדה וכל ביחד פה. פה יש לנו רק 2.
What do you mean?
כאילו, כשגמרנו את המתנגן שם, נכון? היה את החלק של הקינטי, שזה נגיד היה עם ה...
No, there's no kinetic and
לא, לא, קינטי, לא
nothing.
קינטי. אולי כאילו שיש...
There's single body, two body, and maybe three body, but all of them are normal order.
כן, אבל פה אם זה שם סינגל בדי, זה גם סינגל בדי.
No, it doesn't matter. It doesn't matter. When I write, so when I'm, this is a functional. It's not. This is not a product. This is a functional. Okay, it's some function of this thing. Okay, but if you want to see how exactly it looks, just take this expression and write it. Okay, maybe I'll write it explicitly, just that you'll see what I mean. So, for example, this term will turn into epsilon alpha beta psi j plus 1 alpha bar psi j beta. Okay, and so on. And here you'll have psi bar, psi bar, psi psi. Okay.
פעמיים J פלוס 1.
Yeah, one of them is the annihilation of psi j, and the psi bar, the j plus 1 is psi bar. But in the limit, again, the limit that the tau goes to 0, you can actually assign it to a local term, the same j.
אז שני יצרים של אותו דבר.
Yes. Yes. Okay. So that's what you get, and so far it's just a sum. And I'm also writing what is the differential. So this is defined as the product over J and alpha of the real part of psi j, the psi j alpha, and imaginary part of psi j alpha divided by pi. Okay? It's a product of differentials, and psi, because psi is a complex number, it has a real part and imaginary part, and for each of them we do a two-dimensional integral divided by pi. This gives a normalization that is useful for us. Okay? Yeah?
Can you explain again what you demonstrated for a UWI student?
So he asked me, what is this? If I shorten the question, okay?
Okay.
And I told him, when I write this, what I mean by these brackets is that this is a functional of many variables. Okay? If you want to see how it looks, just plug in. I just replace operators by their eigenvalues. That's the idea. Okay? Okay? This is how I go about to get a pattern. Okay, so now I think maybe you're going to see where I'm heading, because so I get here something that if I take the limit j where d tau goes to 0, the sum over j will turn into an integral, right? J is just an index here that counts the time from 0 to beta. And here I have some expression for the Hamiltonian, but here notice that I have a difference between psi j plus 1 minus psi j. Okay, and remember that we want to take the limit that psi j and psi j plus 1 are divided by a small, it's like changing tau to tau plus d tau. Okay? And this is the difference, and we can easily turn it into a derivative in the limit that d tau goes to 0 if we now multiply and divide by d tau. Okay? We multiply and divide by d tau. Now, this d tau, as well as this d tau, can be taken outside of the sum. Okay? And inside, I will get, in the continuum limit, I can replace this by a time derivative of, of psi. Okay? Okay? So let me write down what is the final result. I think I can do it here now. So z is going to be the integral over all psi bar psi, which is now going to be the limit of this product the limit when n goes to infinity, and to infinity, right? Yes. Okay, where j is going from zero to n, and n goes to infinity, and here I have. After I turn this into an integral, I get something that I can write as e to the minus s, okay, and it's an action. This s is an action, and I can write what it is. Because I already redefined it for us. So here, S is an integral from 0 to beta d tau of psi bar d tau psi plus H grand canonical of psi bar and psi, and now I no longer do the distinction between j and j plus 1 because they shrink to a single point. Okay, so the only reason to distinguish between j and j plus 1 is if you have a difference. But if you are in the limit that if you have a product of psi j plus 1 and psi j, it's just the same point. Okay, j is just in the continuum limit, j times the tau is tau. Okay, it's the continuous variable tau. Okay? Okay, so this is the result. Okay, this is the result. And there's one thing I forgot, not forgot, but I'm now mentioning. There is, what is the boundary condition on this integration? So I'm integrating over all the fields psi of alpha tau, if you like. But there is a constraint that, and it comes from this periodic structure, that psi of 0 equals psi of beta. Okay? So I'm integrating over all the possible trajectories that go on a circle of length beta in the tau direction. Okay? And what you have here is just the expression for the Hamiltonian. Okay, so I can put it in the box because this is now a final result which is general. Okay? So let me once again explain what we're doing here is we are defining an action that is a functional of the field psi, and every time I remind you that psi is not just one number, it's a vector. Okay, it's a row or a column of all the psi alphas, but alphas are quantum numbers of the single particle states, and it's also actually, let me write it like this. So psi of tau here is okay, and this runs on all the possible alphas. It's an infinite column, and psi bar is an infinite row of the same thing. Okay, and these are local fields that they depend on imaginary time and on some index alpha. Okay, and we are integrating over all the choices for all the taus and all the alphas of something like this that we could write as an integral over complex numbers. Okay, so this is what it is, and it's always a scalar. Okay, so this is the general formula, and now let's see what we can get for it in some simple case. Okay, just okay. And there is one, okay, so there is one step that I want to do further. So that this is one way of writing it when you work with the local fields psi of tau. But as I'm emphasizing, this tau, this imaginary time, is going in a circle from 0 to beta, obeying periodic boundary condition. And because of that, we can expand it in Fourier components for a periodic function, right? So psi is a periodic function, you can think of it like this, with period beta, periodic function of tau. Now, why do I want to go to do a Fourier expansion? Because when I look at this expression for the action, so here the Hamiltonian will just be products of psi bars and psi, okay? That's what it's going to be. And they're all local. They're all local. They're all in the same tau. But here I have a derivative. And usually when we have a derivative is a non-local thing, so we want to go to Fourier space. Okay, so we want to go to Fourier space in the tau direction, the tau axis. And because it is periodic, we can expand psi of tau as, and this is for each alpha, okay? We can define a Fourier series it's a Fourier series, not a Fourier transform, because it's a periodic function with a period beta. And what are the omega n's? They're going to be multiples of the basic frequency, which is 2 pi over beta, right? So omega n is just n times 2 pi over beta. And beta, remember that beta is the inverse temperature. So it's actually 2 pi n times the temperature. This is all in units where, remember, h bar and k Boltzmann 1, so frequency and energy have the same units, and temperature. They all have the same units. Okay? Okay, so this is a definition of, there's some expansion in Fourier components. And the inverse transform is that psi n is 1 over square root of beta of integral d tau from 0 to beta of psi tau e to the I over n. Okay? Okay, so these frequencies are called Matsubara frequencies. Okay, and they are basically multiples of the temperature, or multiples of the temperature times 2 pi. Okay. Okay, so why is it useful to plug it in here? Because this term, after if I express the psi tau in terms of this sum over psi n, the first term will give me something that is diagonal in the index n. Okay? Okay, so let me show you how I use it for a simple example. This I can already erase. And let me write down, just repeating the I'm just copying it here because I want to use this thing for an example. Psi n e to the minus I omega n tau. Omega n is 2 pi n over beta, and psi n alpha is, sorry, integral over tau. Now I can erase it. I just copied it. Sorry that it's disorganized, but I want to keep this the definitions here. Okay. All right. So let's now take a simple case where I have a non-interacting Hamiltonian. Non-interacting Hamiltonian, then let me call it H0, okay? H0 is just sum of alpha beta, epsilon alpha beta, A alpha dagger, A beta. And therefore, the grand canonical H is going to be, so I'll then write the action S naught is the action that I get when I plug in this Hamiltonian here, okay? So I first write it in terms of the size of tau, and I have psi bar d tau is, to write it more explicitly, is the sum over alpha of psi bar alpha d tau psi alpha. Okay? And then I have plus the sum over alpha beta epsilon alpha beta psi bar alpha psi beta, and both of them are local functions of tau, and minus mu sum over alpha psi alpha psi alpha. Okay? This is S0. This is a single particle Hamiltonian with only single body term. Right? And I here use the definition of the grand canonical Hamiltonian. And writing it in this expression, you can already see that if I choose the right basis, so I wrote a very general single body Hamiltonian, but if this is all you have, then the choice of the basis alpha is can be optimized by choosing a basis where this is diagonal, right? And then we'll have just a single sum over alpha of A alpha dagger A alpha, and the index alpha will run over everything, okay? So we'll do it in a second, but before I do it, I want to show you why I decided to switch to the Matsubara frequency representation. Let's plug in, let's look just at this term. I have an integral d tau from 0 to beta of, and I'm taking just one term in the sum, psi alpha bar d tau psi alpha. And now, when I plug in the expansion of both of these in terms of their Matsubara frequencies, I will get 1 over beta times psi bar of, sorry, I have a sum over, I'll have a sum over n and n prime, psi bar n alpha minus I omega n, let me put the prime here, omega n times psi n beta, psi n alpha, times the integral from 0 to beta of e to the I omega n prime minus omega n times tau. Right? I just plugged in, for each of these, I plugged in the expansion, and then I have a double sum over n and n prime. Right? This is what I did. But we know what is this. And remember, the omega n's are just multiples of the basic periods. So it is exactly, it's a delta. This is going to give me, it's going to give me 0 unless n equals n prime. And if n equals n prime, it's just an integral from 0 to beta, so it's just a factor of beta, right? So it's going to give me beta times a delta of n prime. Okay? And therefore, because of this delta, I have only a single sum over n. It's diagonal in n. The factor of beta cancels. And I will get that this can be replaced by a sum over n of psi n bar minus I omega n psi n. That's all. Okay? So it's diagonal in n, and the time derivative turns into a factor of minus I omega. That's all, okay? So now I can do the same also for these two terms, and both of them, because they are just quadratic in psi and psi bar, the local tau will once again give us something that is diagonal in n, right? So what I'm getting from it is for non-interacting particles, I can rewrite the action in terms of, let me see, where I will do it. This I can erase, right? Maybe you want to take a photo and then erase. Okay. Actually, it will be not a bad idea to repeat the calculation yourself, but anyway, everything here is recorded, so no problem. So we're getting that we can rewrite it as follows. The whole action, S naught, can be expressed as a sum over n and alpha, of n, let me write it as n and alpha and beta, because this term may not be diagonal in alpha of psi alpha bar times. I'm collecting everything together. There is minus I omega n minus mu times delta alpha beta plus epsilon alpha beta. All that multiplies psi beta. Okay, this is what I get. I'm collecting, these two terms are also diagonal in alpha, that's why I have this delta. And epsilon may be something general, okay? So this is the expression for S naught, but I can do better. I can do better by choosing my alpha more smartly, that epsilon will also be diagonal in alpha, because if we just have a single body Hamiltonian, there's usually no reason to work in a basis that is not there. Okay? So this is what defines what we choose to call alpha. So if in addition epsilon alpha beta is actually epsilon alpha delta alpha beta, the whole expression becomes completely diagonal, completely decoupled to each alpha and each n. And here, sorry, I forgot that there is the index. Sorry, write it more nicely. It's n alpha. Okay, there are two indices. There are two indices. The index n is for the Matsubara frequency, and the index alpha or beta is for the quantum number. Okay? That's good.
This is only for S naught, right? If we
Yes, yes, and we'll get to what happens to the interaction. So that's why am I doing this? Because you see, if your Hamiltonian is single body, I will shortly show you that you can actually exactly calculate the partition function. You can solve it, okay? But once you put interactions, then you cannot solve, usually you cannot solve exactly, and then you have to do either a perturbation theory or some trick, or there are lots of tricks. But first, the single body alone is exactly solvable in a very simple manner. And from this, you can actually get everything for a free. What is the case where the Hamiltonian is a single body? It's just a free gas. Okay, that's what the free bosons are. So everything you know about statistical mechanics of bosons should come out of here. Okay, so I think this I can erase now, and let me summarize what we got for non-interacting bosons. Okay, what I got is that we call it Z naught for non-interacting, is going to be an integral, and now I want to write the differential. I want to write a little more carefully as the infinite limit of the product of J going from actually no, we can let me write it much simpler way. It's a product over n and alpha of d real psi and alpha, d imaginary of psi and alpha, over pi and beta. Why did I divide by beta? Because the psi ends, so if psi tau is a factor of 1 over square root beta, okay, psi n blah blah blah, so the psi ends have dimensions of, as opposed to the psi's, they have dimensions of square root beta. So when I do the integral over psi and psi bar, I want to divide by beta. Okay, this is just to set the, you want this to be dimensionless. Okay, that's why I have to divide by beta for each term. Okay, otherwise you get something with the wrong dimensions. Okay, so that's the definition of D, and if you write it in terms of the Matsubara indices. And now I have e to the minus s naught, where s naught is now just a sum over n and alpha of psi bar n alpha minus I omega n minus plus, let me write it like this, epsilon alpha minus mu psi n alpha. Okay? Okay, it's a sum, it's an independent sum of quadratic things. Okay, each term on its own. Okay. All right, so I'm claiming that we know to solve this integral. Because what is it? It's nothing but a multidimensional integral of simple Gaussians. All right? Let me write here a formula. Let me write here a formula that in your homework, I think you're going to prove it. So if z is some complex number, z is x plus iy, then if you have an integral of the form and actually let me write something even more general. I want to see. I'm writing a general integral, but we're going to solve it now for a simple case. I'm also allowing a linear term here of the form v z bar. Okay. And here d z bar z is defined as dx dy, the real and imaginary part, divided by pi. So the result. Okay, I didn't notice. So, okay, so the result of this integral is just 1 over w times e to the v w minus 1 v. Okay, that's a complex integral, and you can easily prove it by just plugging the definition of z and z bar in terms of the real and imaginary part. It's a double Gaussian integral. Okay, so that's a useful formula. Now, in our special case, what do we have here inside the Z naught? we have here in the exponent is just e to the minus a sum of such quadratic thing, but because it's decoupled to a sum over all n and alpha, we can write it as a product of over alpha and n of exponentials of a single variable, right? So in other words, z naught is an integral. I'm writing it explicitly. A product of over all n's and all alphas of the real psi n alpha, the imaginary of psi n alpha divided by pi beta of e to the minus psi n a, that we call it a n alpha, psi n alpha, where what is this a? This a is all of this I call a. Okay? It's just a number which contains dependence on omega and epsilon. Okay? So I have a product of independent Gaussian integrals. And the answer is just each of them will give me, because it's just a Gaussian integral without the linear part, it will just give me a factor of 1 over w. In our case, the w is just this a, right? So it's going to be just the product of all the n's and all the alphas of 1 over a times beta. So it's minus omega n plus epsilon alpha minus mu. Okay, and we just multiply this. It's a product of these things. Okay. Now, actually, there is a more general way of writing this such a Gaussian integral. If so, here I chose a basis where everything is diagonal. Okay, but I can prove a more general formula if we have a field psi that is a vector. Okay, so it's so generally it's a vector. It's not just one complex number. Then the Gaussian integral e to the minus psi bar a, where now a is a matrix. Okay, this is given by the determinant of the inverse matrix. Okay, that's a more general formula, which actually we kind of proved here by going to a diagonal basis. Okay, if you like to prove that this is correct, you have to diagonalize the matrix. This generally gives you some n and n prime, and A is a matrix with 2 indices. Okay? But if I choose the diagonal basis of the matrix, then the determinant is nothing but the product of all the diagonals, of all the terms on the diagonal, right? And that's what we get here, right? But if you want to be more general, this is...
Efrat, what do you have a factor of 1 over beta here and not in the...
Yeah, because the reason the factor of beta comes because the fields psi have dimensions. Okay,
Here they don't have...
So here, yeah, exactly. Here you don't have it. That's why you just get a determinant of A. Okay? And here you see the beta is not inside the A. It's outside, but it's there for each term. And because it's there, once the A inverse is 1 over something that has units of energy times beta, that's dimensionless. Okay, so it sets so the overall thing is dimensionless. Okay, there's an extra beta. Okay, so this is the partition function of a free gas. I don't know if you remember or saw it before in the courses. But from this we can calculate all sorts of thermodynamic quantities. For example, okay, so one of the things that we can also compute very easily is, let me see what I want to erase. I think this I can erase for now. Okay, I want to leave this one actually for now. So I can define, let me define a Green's function. It's a matrix, and it's definition is an expectation value of psi bar and alpha, psi and prime beta. Okay. This is a Green's function. It describes, describes the probability or the probability amplitude to have an overlap between annihilation of state beta to creation of state alpha. And what I mean by expectation value is just its definition in statistical physics, which is 1 over z times the integral d psi e to the minus s times psi bar and alpha, psi and prime beta. Okay, that's so the definition for any operator, the expectation value is defined as 1 over the partition function times the action times the operator. Okay, that's just the definition of an expectation value, right? Okay, and here the operator that I want to average over has to do with this combination of fields. All right. Now, what is it? So if I'm looking at an action that is free, that is S naught, and it's quadratic, then let me write it like this. So if S naught is of the form, I'm writing it very schematically, it's some quadratic form, psi bar psi with some matrix A. Okay. Then once again, the calculation of the Green's function is just a simple Gaussian integral, and the result is that G naught is n alpha, and prime beta is nothing but the inverse, the n alpha n prime beta element of the inverse matrix. Okay, and this is also an integral that you can prove it. Okay, you can prove it mathematically. I'm not doing the calculation, but if you just take this definition, this is what you get. Yeah?
The order between sides in brackets are...
The order is not important because there are numbers. That's what I try to emphasize. The main advantage of the path integral, forget about the commutators, they're all hidden in the process that we did. Okay? They're hidden there, definitely. That's the reason why you get the time derivative in such a way and all that. But in the end, you get something that is just a complex integral. It's not multidimensional, but it's complex. It's just numbers. Okay, so the order is actually not important. But of course, if you want to write it, okay, if A is not a diagonal matrix, then what I mean by this is just the usual thing. Right? It's a scalar that is combined from, yeah, right. Okay, because this is a row vector, sorry, a column, and this is okay. Great, okay. Now, if A is also, if you choose a basis where A is diagonal, then also G will be diagonal, and it will be just 1 over this omega. So let me write it down. Running out of time. This I can already erase. But before I write it, before I write it in the case of the diagonal, notice that this is completely general. If I have an action defined by quadratic form with some matrix A, the Green's function is, here I wrote a particular matrix element, but you can also define it as a matrix relation, which is that G naught matrix is the inverse of the matrix A, right? It's the inverse of the matrix A. And therefore, because of that, I can actually rewrite my action S naught. Instead of calling it A, let me just call it the inverse of G, okay? So, you can write it like this, where G naught is the Green's function, okay? It is just inverting this relation. Sorry, here I put the index, just for not to confuse you, put the 0 index here. But it's the same thing. This is the matrix element of that G naught. All right. So this is a matrix. This is a matrix, not necessarily diagonal. Okay.
At this point, why do we need 4 indices for describing the matrix?
Because we have in the general case, actually, if this is because the Matsubara is always diagonal, then you're right. Actually, this is diagonal in N, right? It is. I'm just defining it in a general way, but you are right. It's always diagonal in N. Okay, and yeah. So in fact, G naught N alpha N prime beta is indeed delta N N prime, and then it's actually, let me write it explicitly for non-interacting particles. It's sorry. Actually, let me write it in the diagonal basis, okay? Let's not make it a mess. Yes, so if everything is diagonal, G is diagonal in both alpha, beta, and in N, and it's given by the inverse of, okay, it's the inverse of omega. So interestingly, notice that what is this function, Green's function, describing is a function, it's a complex function, which has a pole, okay? And when does it have a pole? When the energy compared to the chemical potential equals the imaginary frequency, okay? And if you analytically continue it to a real frequency, it's actually describing the energy of excitations, okay? Okay, so, okay, let me just show you two more things and we'll finish with it. So, yeah, I'm leaving this. Okay, this I don't know underneath. So let's look at, for example, on some physical quantity that we can get out of this calculation. I defined here a Green's function, but this is a quantity that is not very intuitive to you because it's written in with some Matsubara. It's something mathematical, but we can get from it a physical quantity that is familiar to us, the occupation of a state alpha. What is the occupation of a state alpha? It's it's actually the expectation value of right? I mean, it's actually the expectation value of the operator, A alpha dagger A alpha, but in terms of the path integral fields, this is what it is, okay? So I remind you that N alpha operator is just the number operator for state alpha. So we want to calculate this expectation value, but when to take the expectation value, we have to represent the psi tau in terms of the Matsubara frequencies. And we see that basically what it is, it's 1 over beta of sum over n of psi n alpha psi n. Okay? This is what it is. And this is I get by just plugging in the Fourier transform, the Fourier expansion, and there is a delta when I take the expectation value because I only get, because the Green's function is diagonal, okay? It has this delta, okay? So, but what is this? This is nothing but what we call the G of n, or let me write it explicitly. So it's going to be 1 over beta, sum over n of 1 over minus I omega n plus alpha, epsilon alpha minus mu. Okay? So, and where omegas, I remind you, are 2 pi n times beta, times, 1 over beta. Okay? Okay, so this still doesn't look familiar. Okay? So you need some mathematics to solve. This is a sum, this is an infinite sum over all integers n. Okay? If you plug in this definition of the omega. And I'll tell you what is the result, and because it was supposed to be done by SAR, but there will be no time to do it in class. So it appears in the handbook of the tutorial handbook that we posted, if you want to see the derivation. Right? But this kind of calculation, this kind of sum is called the Matsubara sum. And by using complex analysis, you can solve it. And can you guess what will be the answer?
1 divided by 1 plus exponent something.
Almost, yeah, you
like,
remember correctly.
Bose-Einstein.
Exactly, so it's going to be,
Yeah, absolutely.
hocus pocus. Okay, sorry that here I jumped a step, but it's going to give the Bose-Einstein statistics. By the way, this year we are celebrating the centenary of Bose-Einstein, the paper, the publication, and next week I'm going to India to a conference dedicated to this. So this is a very good time to finish the course.
In India,
In Kolkata, in the Bose Institute, named after NS Bose, yeah. So this is what you get, and of course, from the partition function, you can also derive all the other thermodynamic quantities that you're familiar with, that give you the Bose statistics and also the Bose-Einstein condensation if you do the transition of what happens at low temperatures. So I just want to end here with some note about the interaction. So I showed you that for single particle, if you have just a single body Hamiltonian, the path integral for bosons give you just it's something that you can solve exactly because they are all Gaussian integrals. And the most important thing is that you have this decoupling to modes, to all the Matsubara frequencies and the quantum numbers are separable. They appear just as an independent sum, meaning that it's like an ideal gas. Okay? What is the problem with an interaction term? And let me just show you this and we'll stop because I don't have time to do anything with it. If you have an interaction term, the interaction is a four operator thing, right? So if I'm writing it, the interaction functional is something like 1/2 the sum over 4 indices. And there are some coefficients. Here I have sidebar alpha, beta, gamma, and delta. It's a product of 4, and all of them are on the same tau. The same tau. And in the action, we have to integrate it. We have to integrate it over, this is if you like V of tau, we have to integrate over all tau. So inside the integral over tau, I have a product of 4, not 2. Now we saw that when we have 2, and we expand them in Matsubara frequency, we get a delta, which gives you just one sum over n. But if you have 4 operators, it doesn't work. Okay, so if you expand each of them in their Matsubara frequencies, you get 4 sums. And the integral over tau will only give you one constraint. So you'll get something like that. You'll get sum over n, n1, n2, n3, n4, and an integral d tau of the exponent of omega n1 plus omega n2 minus omega n3 minus omega n4 tau. Okay, and this once again will give you a delta, but the delta will only set n1 plus n2 equal to n3 plus n4. So you're only eliminating 1 out of 4 indices. So you still have a mixing between different Matsubara frequencies. And then everything, even though in the time domain, the imaginary time, it's local, in the Matsubara, it's not. So that's that's already showing why is it complicated. Well, it's one of the reasons, of course. But there are a lot of tricks how to treat it. And the fact that we can solve integrals for just complex numbers is very useful. Okay, because any perturbation theory will give you an expansion over integrals that you can solve, and it's very well controlled. Okay, so there's a lot of progress you can make, and I'm sorry that if we had one more week, we could learn more stuff, but everything that I didn't have time to cover is in our notes. Okay, it's posted either in my notes or in Yaakov Yudkin's notes that are in the tutorial book. So yeah, that's all I have to say for today. So thank you for the attention and sticking through the whole course. Good luck. And we'll be in touch during the education before the exam. I'm available for questions. I'll have some office hours, but just keep following the online. Keep track of the course website for announcement. Yeah, you wanted to ask something?
No, I ask, this is the last lecture.
Yes.
No.
The semester ends. The semester ends in the middle of next week. Yeah, and Sarah is going to give the tutorial now. Will be the last tutorial.
Now?
Yeah. 6. Right.
But we have it's ended in 9.
No. No.
Check.
Yeah. That's not what they said.
No, they said that you can't teach new material in the last
Okay. So in my case, I will be in India.
Yeah.
So I will not be able.
I
I will not be able to teach, but to make up for, I mean, we are supposed to have some kind of summary or some reps. We'll have that closer to the exam, okay? So, and which will also be more fresh, will bring you fresh to the exam. Yeah, so I apologize that this course is really short. Even before we have to cut it to 10 weeks. And now it's even worse, but I hope you learned something, and whatever you learned, you will apply in some form. Okay, thank you.
Thank you.
Okay, so path integral. What's our motivation? Very simple, very simply. I have, let's say for example, I have two locations Z, I,
Yes, I'm
to the F, and I have a particle starting in XI, going to XF. Right? I want to find the probability of my particle going from one spot to the other. Z is just a location in one of the axes.
אפשר להתחיל מהרקע?
No. Okay. So the probability, we'll just write it in the quantum method, the quantum index. P I F. Notice that that here we read this from right to left, so don't be confused. This is a particle going from I to F.
Like an equal,
Yeah. Okay, yes.
Yes.
Good. Okay. So, if we can't really calculate it directly, but let's just for a second put here put in some blocker inside with 2 slits. See what happens. One slit will be A, one slit will be B. And now this probability from going from I to F will have to be going from I to A to F or going from I to B to F. Okay? Equal to F A. Sorry, this is absolute value square. This is absolute value square here because this is full statistics probability. A plus F B.
Sorry, it's F or T?
F.
All? It's F?
All of them is left. The curve is in the top.
Ah.
Yeah, the curve is in the top. All right. So we added some board in here and reduced the number of paths that our particle can possibly take. And basically, what's written here, just to reiterate, you're going from I to A, and then from A to F, or we're going from I to B, and then from B to F.
מה זה? זה חורים כאילו? A,
Yeah,
B?
slits.
Slits?
Yeah. Okay. So now to expand this even further, eventually we want to reach a continuous limit. Basically, having all the possibilities. So next, I'll just add some holes. Instead of calling them A and B, I'm going to give them numbers. Minus n plus 1, 0, minus 1, 1, n minus 1, n. Okay, I gave the slits numbers. And now, so this here will have, this goes to a sum. I don't want to write the absolute value squared every time, so I'm just going to go like if I will go to sum over n, if n I. It's basically the same thing here, except I increase the number of holes. Now, I can increase the number of holes until this entire column will be continuous. But the next thing that needs to change is the continuity in the z direction. How we do it? How are we going to do this? I'm just going to add. And let me do it in different colors. Easier to see.
Ouch.
You're welcome.
רגע, מחקתי את החורים.
הנה, חזרו. And so on. Well, I'm also going to number this one, like 1, 2, 3, and so on up to n. And now, I can expand this fi to have a sum fi n of n, n of n minus 1, n 1 of f n n plus, no, or plus, and m minus m minus 1 and 2 1
Can it go back and forth in the calculation? Like it can go to Zm and go back to Zn minus 1 before it.
This is just a simplified example. In a real space, yes. Here you can just take z to be, for example, the time space. For example, you have a one-dimensional particle, can go back and forth, but we look in each cross-section in time.
So that is like time here?
It can be like time, yes. Just to simplify this, okay? So we took a very discrete equation and expanded until we get into the continuous form, when we sum up all the different paths. I can go from the xi to the top hold and to the bottom hold and so on, and I sum over all of these paths, and this will give me the probability to go from xi to xf. Now, there's a lot of magic in the background, math magic, that gives us the propagator. It is a function of the time difference, the starting location, the final location, which will be too bad. I mean, I can do G. I don't mind.
No,
You prefer G?
No,
everyone?
it's just that for everyone G and K are same.
Right. Okay.
About G.
Do you want me to use G instead of K, instead of kappa?
I not understand what.
Why? Efrat use a different letter.
Ah,
Do you want me to use the same letter as Efrat or the same letter as my notes?
it's not Meshoni.
Okay. Okay. Of course, in this notation, it's all has all of this sum up to a continuous limit, and where P, our probability of going from xi ti to xf tf equal to kappa absolute value squared. Kappa, of course, is all of these indexes. Now, some smarter people than I, pretty sure Feynman, found that this propagator can be generalized as k, xf, xi, t equal to integral x e to the I divided by h bar s x. Well, just write everything. Separate. where S is the action, equal to integration from Ti to Tf dt of 1/2 m x dot squared minus v x. Capital nu, I'm pretty sure that's how you call this quickly. It's just a normalization factor. It's equal to m divided by 2 pi I h bar delta t. All of this to the power of n divided by 2, where n is like the number of separations that we use, and capital dx equals xn. Of course, just integral over dx minus 1 over dx n minus 2 over dx2 integration over dx1. Yeah, so it seems very daunting. We have an integration over time over different x's that can have different value. So it's like an integral. The x depend of t and the x depend on your axodic integral. It's very complicated.
יש לי שאלה לא קשורה.
Okay.
מתי שיעור חזרה? יש תאריך?
No, I don't have a date yet, but it will. I will publish a survey, a poll, to make one. It won't. It will. I'll try to aim it to be like 1 week, 2 weeks before the exam, so relatively close.
This is for zonic or general?
General. We don't really go into this in this tutorial. If we had one more tutorial, we would go into this entire subject. So it's general. Okay. By the way, if we'll take here h bar, just an extra something that's in my note. If we take here h bar equals 0, we'll get a fast oscillation, and which will converge into the classical solution. Yeah. Yeah, but it's a constant because we live in a world where h is a constant. I'm saying if h bar, if you'll find one day that h bar equals 0, we'll just see that this entire calculation will it will take some time, but we will see that this entire calculation will converge into the classical solution action method.
אבל אם h גג דבר של 0, זה פשוט מתפדר, מה שיש שם בארגומנט זה מתפדר, אבל פשוט יקזז את עצמו בעניין 0 מוחלט.
No, there's some limits that you need to do here. I don't want to really go. There's a small explanation in the notes, in the tutorial notes, but not really much about all the. Yeah, all the non-classical trajectory, all the trajectory that don't minimize s will indeed cancel out.
Oh, okay.
The trajectory that will minimize s will be like 0 divided by 0. Okay. So this is just the equation that you'll use in this chapter. So let's just do two exercises. First of all, free particle. first interpretation, we're going to take this potential element to 0 and just be left with s equals integration over half m x dot. So t. Oh. Integration x t to the I divided by h bar integration 0 t dt squared divided by 2 times m. I'm sorry, I don't have space. Now let's look for a second this small integral alone. We know that if we'll take this continuous integral and change it to our discrete location xn, so x dot will be equal to xn plus 1 minus xn divided by delta t, and integration dt will be equal over n delta t. So overall, this integral here will just be sum, or I'm going to write it in a second. Yeah. Okay. Dxn e to the I m q bar. Just in the Judkin's notes, there's a divided by delta x here. I'm pretty sure it shouldn't be there. Just notice, watch out for it. I'm not gonna write it because I don't think it should be there. Out of x and oh, yeah, it should be there. Sorry, because there's a square here, so there is a delta t in the denominator.
Justin. Justin.
Yeah.
Thanks. Wait. Thanks.
Oh, Macarena.
And you need to raise the television.
They need a new one anyway, it's fine.
לא,
לא, אני לא מחליף, זה זמני, אני רק פנה לי מקום.
שפת סימנים.
What you said, there is a difference in notes and what you wrote.
Hmm?
You just now said that there is some.
Oh, no. I made a mistake by saying there's no delta t here. Because it's x dot squared, so there's delta t squared times delta t. Right? I'm just going to open it so it will be a bit clearer. Equal 12 over dx n minus 1 dx1 of e power of I and there's the normalization factor here. And 2 h bar t x x1 minus x0 squared plus x1 minus x2 squared plus x a minus 1 minus x n squared. Okay, just opening the sums, all the sums and multiplication. Alright, so let's do this integral one by one. Start with x1. Right. I1, I'm going to call it I1. x1 is the integration from minus infinity to infinity dx1 e I m divided by h bar 2h bar delta t of x1 minus x0 squared plus x2 minus x1 squared. Let me just I'm just going to open up this part here. I'm going to call it R because I want to. R is equal to x1 squared minus 2 x1 x0 plus x0 squared plus x2. I'm just x1 x2 2 plus x1 squared. I can rearrange this equation to be equal to 2 x1 minus x0 plus x2 divided by 2 squared plus x2 minus x0 squared divided by 2. You can open this up and check for yourself if you don't believe me. Can I erase the...
No.
Wow, so rude. Just no. What about please and thank you? Alright.
You're welcome.
Thank you. Alright. Now I'm gonna change. Make sure it's not gonna close the weekend. Now we're gonna do the transformation. U is equal to x1 minus x0 plus x2 divided by 2. No, nothing. Like this. Okay. So what we're left with is I1 equals E of I n divided by 2h bar 2 h bar 2 t x0 minus x2 squared time ratio of minus infinity to infinity e to the power of I n h bar delta t squared, which would just be solution for this integral would be square root of 1/2 2 pi squared by m h bar delta t e to the I m to h bar delta t x2 minus 0. We ended up with something very similar to what we started with, just the move just instead of having an x1 between those, was no x1. So that's it. Right, let's do it again for I2, and then we'll just conclude with saying the overall formula. This will, you can clearly see this will go to recursion, right? Here we remove the x1, and the next one we'll remove the x2, and we'll have x3 minus x0. Yeah. Let's do it.
בעצם ככה רוצה לדעת בעצם, נכון? כאילו, איך רוצה לדעת x0 מינוס x2 החוצה ברגוע?
הוא לא... לא רשמתי פה.
רגע, איך רוצה לדעת
du, קודם earlier du was x1. So everything that's not dependent on x1, you go outside.
אוקיי, אז בעצם פשוט פתחת את הדבר הזה והעברת להציל את כל משהו לא תלוי?
Yeah.
ומה שכן היה תלוי עשית את ההצבה הזאת.
So, I2 equal to equation of minus infinity to infinity. E to the I, I really should have just given this constant a name. Delta t, 1/2 x2 minus x0 squared plus x3 minus x2 squared. This can also be rewritten almost like we did here. I'm not gonna do it fully, I'm just gonna give it the answer. Two. Very similarly, by changing our integral, you can get just finish this equations off. 2 divided by 3, 2 pi I h bar t divided by m is the power I m 2 bar 3 delta t x3 minus x0 squared. Right. And now you can see that from the 3 here, divided by 3 here, when we integrate on over x3, instead of what is it? Where is this? Instead of divided by 2 here, it will be divided by 3. Right? Here, the x2 came from the divided by 2 delta t. So the next one will be divided by 3. So overall, In will be equal to integration over d n e I m to h bar delta t 1 divided by n xn minus x0 squared plus xn plus 1 minus xn squared will be equal to e the I n divided by h bar n plus 1 delta t n plus 1 minus x0 squared times integration infinity xn of e of I m by 2 bar delta t n plus 1 by n xn minus 1 divided by n plus 1 x0 minus n plus 1 xn plus 1. Overall, In will be equal to n divided by n plus 1, 2 by 9 h bar delta t divided by n e to the power of m h bar plus 1 delta t n plus 1 minus x 0 squared. Can I rest the left side?
No.
Okay.
Yes.
Thank you.
You wait.
By the way, this is like going like a little bit fast. The tutorial notes is even longer because there's a lot of explanation that I say loud. Okay, so overall, we know that kappa xf xi no, is equal to, first of all, the normalization factor, then square root, all these square roots multiply together, so 1 over 2 times 2 over 3 times 3 over 4, and so on up to -1 divided by n. Times 2 pi I h bar delta t divided by m square root to the power of n minus 1. This times e to the I m 2 h bar t xf minus xi squared. No, we're not done. We're done. This one can be reduced a little bit, and overall, right. Overall, I'm also gonna say t equals n times delta t. This right here, we see that the 2 cancel out, the 3 cancel out, the 4 cancel out, also the n minus 1 would cancel out, so it's just going to be square root of 1 divided by n. Then delta t divided by n, oh, yeah, we also have to put in the normalization factor. So I'm just going to write it again, just so we have all the pieces. No? תיקח לו מימין. overall, if we put everything in and organize it, kappa xi t equal to square root m divided by 2 pi I h bar capital T e the I and 2 divided by h bar T f minus whew. Anyone
Maybe
comments?
maybe the square root shouldn't be there.
I don't know. Well, here it should be.
No, in the where you have to the power of n minus 1, because then maybe it's no.
This? Here?
Yes, because like
Okay, that's n minus 1 divided by 2 if you cancel the root, and then this is minus.
So this times this one will just give us 1 divided by 2. So that's why there's only a square root. Minus 1 divided by 2. It's the same, it's constant. Sure, thank you for noticing. Anyway, we see here that if we take this with the absolute value squared, we have equal probability to be anywhere in space. Which makes sense. This is the free particle. There's no constraint on it. Remember?
Equal probability.
Yeah, you remember that P from the start of the class, P equals absolute value of kappa squared. So the absolute value squared of this function, this exponent will disappear, and we'll have some gain here. This will be just the absolute value of this square root.
איפה מה אנחנו נשים בחזקת n חלקי 2 של השורש שני סולמית I, H בר?
איפה? מה?
אמרת משהו לגבי השורה הראשונה, השורה הראשונה כן, אמרת שיהיה פה משהו שילך בחזקת n חלקי 2 פה, למעט
Alright, let me do one change that I think will make it clearer.
Now it's correct.
Thank you. Thank you. Thank you.
No,
And now multiply it. Huh?
It's a question.
Oh yeah, now it's correct. Yes. No, it was correct even before. Don't try to trip me up. Right? And then this one would also almost cancel out with the normalization factor.
כן, הוא כמעט כזה, זה מעט אחד שישאר שם.
Alright.
יש סולמית או פאי, בתוך הדבר הזה של השורה הראשונה.
Neither. What?
בשורה הראשונה יש 2 כפול משהו, כפול I.
Pi.
פאי.
Uh,
מה אתה עושה?
maybe. I don't know. Okay. Now I'm going to introduce to you another method of solving these equations.
yay.
Woo-wee! With an even more complicated question.
Are we going to finish soon?
What? There's another
45.
another hour. I didn't hear no bell. You know, I want to. I think I'll hate teaching at school if I ever go there, but I want to do it just so I can tell the class they're not dismissed. Just so I can tell them, you have to wait till the bell. And then when the bell comes, I'm not going to let them go.
You can come with a gong to here.
Yeah, but here you're 3 people. In school I can just make them stay and learn more. Study more. Suffer. Alright. Suffer. Now we're doing the harmonic oscillator. As an example, just to remind you, of course, you already know that the Lagrangian of the harmonic separator is 1/2 x dot squared minus 1/2 m omega squared x squared. Right. Now this problem is a bit annoying. We can definitely solve it in the way that we did before. It would just be very long and a little bit more complicated. Also, but we also have here a little problem that we have two different order in the derivative in a squared equation to the power of 2, which is, as we know, it's a differential equation that's differential equation. It's the basis for differential equation that's very hard to solve. So this exercise I'm going to solve with a few tricks. Yeah. You can do it as we did before. It will be long. We can try to solve this by solving for x. No, that's it. It's going to be long. Very long. We're going to do it a bit of a different way. It's still going to be long. Don't worry about it.
What you say?
Yeah, whatever I said.
And we use imaginary time only with the partition function?
We don't use imaginary time here at all. Yeah, specifically. I'm not even sure if you're going to need this in this chapter at all. And back. X of and divided by 2 bar integration of ti df dt psi squared minus omega x squared. Right. Now we're going to use a method that's called decomposing the propagator, which says that we can take our location, xt, and separate it to classical solution, t, and the quantum fluctuation. Okay? Right? This will it's almost like saying it's separated to average and fluctuation. Okay. Now, the classical solution we already know is x2 dot c equals to minus omega x omega squared x c. This is the classical constraint for an oscillator, and because we're starting in a well-defined location, xi and xf, I can say that x of ti equal to xc ti, and x of tf equal xc tf. I'm starting in a well-defined location and I'm ending in a well-defined location. So there's no, so the quantum part of the location in the beginning and the end is 0.
When does this end?
You want to go home so badly? I mean, it's free country. You can leave. Like 7.5 plus minus, depending how long it will take us to do this example. Right.
רגע, אז החלק הראשון זה חלק קלאסי, חלק שני זה פלקטואציות קוונטיות ביחס לחלק הקלאסי. מה הפלקטואציות של חלק הקוונטי אומרות לנו? שזה כאילו לא נמצא בדיוק על המסלול הקלאסי?
Yeah, it basically says that there is the exact solution for the classical case, and then we have sort of some paths around it. It's a path around it.
So it's like you start with the delta function, let it spread out, and then you measure again.
This is always correct. This condition that I put right in here, because we are specifically looking for one location in space and ending in one location in space. We're not looking for like a section space that we can end up in. So if you have a well-defined location, you don't have quantum fluctuation. Quantum fluctuation will be in the trip. I have a nice trip. All right. So Now that we separated this, we can also separate our Lagrangian function, 1 over half m x dot c plus xq dot q squared minus 1 over 2 m omega squared.
אמרנו שם את המשוואה הדיפרנציאלית של x נקודותיים של מינוס מטבע בו x.
This is the known classical solution.
זה פשוט פתרון הקלאסי.
Yeah. You can, if you want to, you can put this in Euler-Lagrange equation. Fine.
Okay.
Where was I? I guess this one. I'm going to open it up. It's going to be. I'm going to open it up and organize it by xc and xq already. So the first one will be 1 over f, 1 over 2 m xc dot squared minus omega squared xc squared plus 1 over 2 m xq dot squared minus omega squared xq squared plus, now there's another term here, x dot c xq dot minus omega squared xc xq. So we have 3 different terms: the classical term, the quantum term, and the interference term between those two. Let's start with the mixed term. We want to find the action, the mixed term, so S mixed equal to m times integration over dt of x dot c x q dot minus omega square xc xq. I'm going to integrate by parts. The first one, so I can move one derivative from q to c. B m should be t minus xc dot xq is omega squared xq. It's equal to integration dt x dot, there's a minus here outside, whatever, x dot plus omega squared xc xq equal 0. Beautiful.
What do you mean when you write mixed integral?
We have terms, the classical term times some quantum term. So it's mixed between the terms.
Can you give intuition why x of q will be 0 at the t final?
What? No, this is equal 0 by the classical solution.
No, where you, what you did
This
there?
here?
Yes.
Yeah, because we're finishing in an exact location. The xq, what it means is fluctuation over space. When we integrate over the x, we integrate it because we can be in every location in a certain panel in time, right? But at the x final, I don't care about all the other locations. I want to know what's the statistic that will reach xf exactly.
But
it's like when you take a measurement. When you take a measurement, you collapse the quantum fluctuation. It's exactly the same.
But isn't xq what gives you the percentage not equal to what? The probability different in 1?
Yep. But in the end, it's nothing. It will affect the propagation in time of the entire function. So in the middle, x fluctuate, but in the end, it's like a standing wave in a resonator. In the end, it's like the constant that we know. Alright. Why did I go back? Why did I go back here? Now that I've separated the quantum and the classical case, we can use some methods that we already know. The classical one, I'm just going to solve directly, and there's an explanation why it will be very simple to solve. The quantum one, I'm going to solve by diagonalizing. And we'll see shortly how. Like we know and love in quantum. Okay, so basically our S will be equal to dt LC plus dt LQ. Alright. So I just SC plus SQ for shorter writing. And now K XF XI T equal to M D X Q. Remember, I'm putting here, I integrated over the quantum x's, because again the classical x's are very well defined, in one spot in each time. One spot in each time, so there's no integration, it's just going to be E to the I divided by H bar SC plus SQ. Now SC, as we saw before, doesn't depend on XQ, so I can take it outside.
עכשיו את S מיקסט, נכון אתה מחשב אותו?
מה?
אבל יש לנו את S מיקסט, נכון? אנחנו לא חשבנו אותו?
Yeah, S mix is this term. Now there's the S classical, X quantum, S quantum.
אז כאילו יש לך שני חלקים שהם לא קשורים אחד לשני, ואז כאילו יש לך את החלקים שבו זה כן מעורבב. במעורבב רואים את זה, אז עכשיו אנחנו קוראים את זה.
ביי H bar. Q. Yeah. Now,
מתחילת רק מה הגבולות של המיקסט?
the mixed.
כן, מתחילת את הגבולות שלנו.
It doesn't matter. It's zero by definition.
פשוט כי היחס הקלאסי מתקיים. ואם הוא היה יוצא אפס, אז חשוב לנו לדעת בעצם תמיד הוא יצא אפס? או ש...
Always, because this is by definition zero.
לא, אני
I mean,
מתכוון...
it will be a constant, but no constant. No constant.
איזה קרוב?
Actually, there's no constant because there's limits to this integral.
לא, אבל כאילו יש מקרים אולי שבהם אנחנו נקבל לגרנדיאנים ותכן שנקבל שזה לא יצא אפס.
Yeah, I mean, there's many different methods of solving this type of questions. Of course, it's one of those physics subjects where most of the questions are unsolvable, so it's kind of a problem. So you just have to find what's the right method for you relative to each question. There's the method we did before. There's the method we do now. There's also a method that kind of cheats with doing Fourier mathematics, which is fun. I like maybe just me.
Only you.
זה הגבולות.
Yeah.
הגבולות הקוונטים זה בעצם תמיד בין 0 ל-0, נכון? והקלאסי זה תמיד בין ההתחלה לסיום שלך.
What do you mean from 0 to 0?
כאילו אמרנו שכאילו האינטגרל XT, נכון? XQT ו-XQ0, שהם צריכים להיות שווים ל-0.
Yeah.
ו-XT הוא צריך בעצם להתחיל מ-0.
You're sort of jumping ahead to what I was about to write right now.
אוקיי, אז כאילו לא, כי אני פשוט יכול בגלל הגבולות של האינטגרציה.
Right. Since SQ is just measured fluctuation, not actual position in space, this one right here, with you two, don't worry. We can just say that this will be the propagator from 0 to 0. This is my argument.
Why?
Because xq in the beginning 0, xq in the end will also be 0, as it's well defined. We remove the classical term, which is like the offset. So I can say it's equal to this k00. We're gonna calculate this anyway, so don't worry.
I don't.
Don't worry.
And in the exam, which method will be used is
What? Oh, the method in the exam? I'm sure it will be pretty obvious in the exam.
Stop.
You'll do some homework. So you'll get more acquainted to the method, to how to approach this kind of questions. All right. So what I'm saying, it's equal to the general function, general kappa.
You know which questions we will have in exam?
For questions? You want questions? I'm always open to questions. What do you want?
Which questions?
Oh, which questions will be in the exam? I'm going to text to everyone. The questions. Don't worry about it.
In what?
Yeah, obviously. All right. Oops. Oopsie. All right. So now we pretty much care about this integral. So I'm just going to write it. This integral is the one that interests us. Q dot squared minus omega xq squared. This will be equal to, yeah, okay, this, before I continue, this is kind of hard to diagonalize because we have two different odd.
Isn't it just integration by parts?
Yes. No, I'm gonna do integration by part, and then we'll see why it's easier to diagonalize like after the integration by part. Everyone's spoiling my class today.
Sorry.
Stop it.
Sorry.
Not.
It's omega baribour.
All right. Now, let's, before I equal here, I'm going to define an operator, O, which is equal to minus m divided by h bar, d squared t squared plus omega u. And you'll see that if the term here is just x o x divided by h bar divided by okay. So now, if we put everything back into our E, the I divided by 2, so the I TF TT XQ O XQ. Okay. Now for the diagonalization. Half an hour. What? We only have half an hour left. Alright. Anyway. Now, before we continue, you see why I did this transformation, because here there's no way to diagonalize it. We have two separate terms to the square. Here we have an x and some operator that we can some change over x. Right. Now this is a linear equation, so we can diagonalize it. I can write xq, in terms of the eigenvector and eigenvalue of omega of O and t, where O of n t along the n t, take integration dt and delta. Basically just opening it up in the orthonormal space. You can, this operator, you probably saw it in the past, so I'm just going to give you the result of the eigenstate, the eigenvalue of the basis of O, the new operator. So just be 2 divided by t square root sine and by t and on the n equal to n divided by h bar and pi squared minus omega squared. Can I erase the left side? Okay. What's this time? 7. Ooh. Alright, we only have like 1.5 pages. Ooh.
Yes.
Only 1.5 pages. Alright. So now. Operating right equal to and all these 3 constants are not dependent of time, so this with the integration will just give us delta. It's equal to so over an by squared. Yep. Squared is also enough. Right side. Yeah. Yeah? Good. So, after I can also change the indices of the integral, so it should be n e I divided by 2 sum over n along the n So, for each one of these n's, will be an integration of dAn minus infinity to infinity of e the I divided by 2 lambda n an squared. This is a known solution of square root of 2 pi I divided by. Wait, you're leaving? Someone's leaving? Because I have like notes and stuff like that in the end.
Yeah, I'm hungry and I'm not able to concentrate.
Alright, so before you go, let me just give you a little tip. We just do a little small break from this question and give a little tip in facing this question. My recommendation is, first of all, check if there's any possible way that you can diagonalize your system. Because as you see, I just reached like a normal Gaussian integration, and it's nothing. Second option that you probably won't see is try to Fourier transform. Use Fourier transform to get rid of the derivatives in the exponent. And the third option and the last option will be what we did with the free particle, which is doing everything by hand. Trying to find some recursion, some recursion between the xn, and try to expand it over the entire series. All right.
I got multiple shit on my.
The third trick was just what we did in the free particle. We just calculated by hand. It's a long walk. Almost no smart tricks there. Just try to keep everything organized. Okay. So overall. T will be equal to relation factor square root of 2 by I divided by I, so 2 by I divided by lambda 1, lambda 2, and so on up to the square root of 2 by I, lambda n capital N minus 1. Equals to n 2 by I of n minus 1 divided by 2. Multiplication n equals 1, n minus 1 divided by square root of lambda n. Right? I can absorb, I'll absorb this 2 pi I into my normalization factor. Simplicity will be n 1 minus 1 and or minus. Of course, there's also like times the exponent of the classical solution, which I didn't write it down.
זהו, שני פאי I, לא פאי I.
Okay. Now, we can rewrite our kappa here to be kappa over omega. For cleaner. Reminding you that n equal to n divided by h bar squared divided by t we're just expanding on the social a little bit. I'm trying to see, to show what happens with omega, the ratio of kappa. All right, so. 0, 0, 0, T. This is the free particle, B, and of multiplication. Just B square root of 2 pi I h bar T. Should remind you of something from earlier. This one. And the change between the free particle and the particle trapped in the harmonic oscillator, the ratio is B square root n equals 1 and minus 1 lambda n 0 lambda n omega equals square root T squared divided by m pi d squared omega squared equals square root divided by 1 minus T divided by pi squared.
Stop. You can erase.
No, take it back. What's the time? 7? Oh, 10 minutes. Right.
12.
Oh yeah.
11.
So this, thank you. And which is to infinity will just be square root omega t divided by minus omega t.
And this is because we believe you? Why?
It's just try it. It's Lorentzian, I want to say. I forgot the name.
So Lorentzian becomes the thing.
Yeah.
Okay.
All right. Thank you. Thank you for believing me. One second. All right. One. Just be equal to square root of omega divided by 2 pi I c. And overall, k I divided by h bar s classic times square root and omega divided by 2 pi I h bar sinus t.
There should be a square root on the first term there.
Yep. Thank you. For keeping me honest. Alright, now the classical solution. It's a bit shorter. Let's see. Time. Okay, we got time. I'm gonna do it here because I want to start again. Well, it's off. Right. This is a bit easier to solve because we have the classical solution. I'm just going to write down. So t will be f minus xi t. Xi t. And c dot of t to xf minus x. Yeah. Minus xi omega sinus omega t. This is the classical solution. Overall, integration by parts. Well, notice that I just shifted my time from ti to 0 and tf to copy of t. Fine. Yeah, it's values that you can choose. Right. By 1, and you can take 0. Right?
או שמותר שרירותית מותר לפרוץ T1 להיות 1? כאילו...
1?
כן, למה שלא נגיד?
I don't 0.
לא יודע, שואל אם זה מותר לשאול.
You can pick them to be whatever you want. Just indices.
זה משנה את התשובה, אבל זאת אומרת הפונקציה.
No.
אוקיי, למה זה לא משנה? פונקציה יש מספרים, זה מספרים, ולהכין שונה.
Yeah, but this equation will just be the difference between them.
אוקיי, בגלל שזה נגזרת כאילו, זו הסיבה שלנו?
Maybe it will change the phase if it is more complex something, or do we say the propagator is real?
The propagator is not real. It's not real.
It might change the phase or something, but
Anyway, we can every change for us is a constant. And since we're talking about like an element that starts in t equals I, there's no real meaning of like the relative time around it. Just change the name. Nothing happens before t equals t I. Right. And this I can really open it up and calculate this for you. It's very long, so I'm just going to give you the answer. It's equal to m omega divided by 2 x I plus f squared Alright. Overall, propagator square root of omega 2 pi I h bar sinus t omega h bar. I'm not gonna write this again in your dreams. I'm not gonna write SC again. No, thank you. Cool.
You will.
I will? Maybe next year I will. I mean, yeah, sure.
But which CS?
SC?
Which CS? What is it?
Trying to mess with me. I don't. What do you mean by CS?
CS. C with index S. S with index C.
It's the classical action.
error or ball.
Which?
It's this one. Classical action. Just put this ugly long solution here. Imagine I wrote it, and that's it.
Okay. Thanks.
You're welcome. So if you have any questions and something, any blah 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 blah, you can come to me. But now, yes, hello. And I'm gonna in the next week I'm probably gonna send a survey for when it's gonna be the preparation for the exam, the next tutorial. We'll solve the questions from tests in the past. So for now, try to practice the test yourself. So you come with questions or questions that you didn't manage to solve and stuff like that. And you can come and ask questions in the tutorial. So?
רגע, אז עקרונית כרגע זה התרגול האחרון להרצאה. שבוע הבא אין תרגול.
לא.
זאת אומרת, לא יהיה עוד הרצאות, זה התרגול שבוע הבא מבוטל, זאת אומרת, התרגול האחרון שיהיה זה כמו שעת השלמה, שעת כאילו הכנה למבחן. נכון? שעת הכנה כזה, שעת לפתור מבחנים.
כן.
רק אתה תעשה חזרה, נכון? תהיה חזרה אחת ושאתה תעשה.
לפתור שאלות מבחנים.
אוקיי, אני חושב שבוע. אוקיי, סבבה, אז אמרנו שעשינו פה בעצם שתי דרכים של הדבר, נכון? נכון, אני צודק, יש שתי דרכים לפתרון כל האינטגרלים.
יש דרכים שעשינו, כמובן יש הרבה דרכים, כל שיטות מתמטיות.
זו הייתה בעצם, פה התחלנו את השיטה הראשונה, נכון?
פה בעצם יש שתי לפתור ישירים, זה
השיטה הראשונה. רגע, לא.
Ah,
זה הרצאה בכלל, זה הרצאה.
שאלה בינתיים?